Ada Lovelace, and we're very happy to have with us today Nachum Dershowitz from Tel Aviv University. Professor Dershowitz received his PhD from Weizmann Institute, right, and, under Zohar Mana, and then he taught for several years in the University of Illinois at Urbana-Champaign, and since 1998 he's a professor in the CS department in Tel Aviv University. His research topics are varied, including AI, programming languages, analog algorithms, and the Church-Turing Thesis. And he's a recipient of the Herbrand Award in 2011. And his topic for today is proving the Church-Turing Thesis. So thank you very much.
Thank you. This is an ambitious topic, but it's what I was asked to talk about. I do want to say that I'm spending this year in Paris at the Paris Institute of Advanced Studies, or they would like me to mention that. Okay, the technology. Today is Tu B'Shvat, sort of Israeli holiday. Everyone is hoping to see the Shuvia and the snow tomorrow, and that's why I'm dressed in green. The series is in honor of Ada Lovelace and her 200th birthday. And I want to connect what I'm talking about to her interesting discussions back 150 years ago. So she raised at least three issues that are of relevance. One is, what can computers do? What can they calculate? Mathematical calculations, and what else can they do? And whether a computer has a mind of its own was another issue that came up in writings. So if I'm talking about the Church-Turing Thesis, let me define it. So Church's thesis is the claim that some kind of recursion equations, which I'm not going to explain, capture the notion of what can be calculated or computed effectively. And effectively means that people can actually work out the calculation. Turing phrased a similar claim that what are now called Turing machines, but he didn't call them Turing machines, capture, again, what humans can do when they're working mechanically, when they're following rules and acting like a bureaucrat or an accountant. But Ada Lovelace's thesis was that Babbage's analytical engine, which he had designed, which was never built, but the design was a workable design, captures all that can be computed. And she says so quite coherently. And I'd phrase it differently and say that the thesis is that 3 baskets of apples suffice for any and all computable calculation. And we'll see what I mean. But what motivates me to find the right definitions, and this psychologist of mathematics famously said, one good definition is worth 3 theorems. And so the goal is what Harvey Friedman, the logicians, set out as a goal at the beginning of the century, that sometime this century we'll figure out weak general conditions which define what effective computability is, so that based on those axiomatic conditions you can prove Church's thesis, and that's what I'd like to show you today. But back to Ada being her birthday celebration. Her math tutor was the logician De Morgan. She came from a wealthy family, and in 1871, long after she was dead, someone wrote that other than Somerville, who was a well-known translator of mathematics text and a mathematician on her own, Ada was the most remarkable female mathematician. Okay, and everyone talks about her father Byron, which is kind of irrelevant. Her paper, being a 200th anniversary, her papers are being digitized in Oxford and put on display. These are her correspondence, I think, with Faraday. And there are unpublished papers of hers that they don't yet have permission to publish, showing her working with Babbage on mathematical puzzles like the bridges, crossing the bridges of Königsberg, magic squares, and so on. hopefully someday these will get published as well. Now, she worked with Charles Babbage, the inventor of many things. And one of Babbage's inventions was the difference engine, which he never finished building, but his son built part of it and was able to use it to compute pi. The idea was to use difference equations to compute mathematical tables. And De Morgan's wife, who wrote a biography of De Morgan, mentions that when Ada was a teenager and first went to one of Babbage's soirees and saw the difference engine, she was taken in by the beauty of the invention as opposed to all the other people who came by who were more interested in pretty things and gadgets. So
how young was she? Young as she was.
At that time?
Yes.
I think she was around 17. She had her coming out around then when the Queen changed, I don't know, and she met the Queen. This was around the period of her coming out into society. But Babbage had more grandiose plans than the difference engine, and something that he designed called the analytical engine, and he had many pages and pages of description of how this thing is going to work. Steam-powered engine to do calculations. So today they've tried to build pieces of it. Presumably the design works, but to get the mechanical engineers in his day to get it working was hard. So 1864, anyone who wants to know how the analytical engine was meant to work should read Ada's description. Lady Lovelace's translation of Menabrea's memoir. Well, and then you'll understand what the abilities were of this machine that had to design. Now, Menabrea was an Italian general, engineer who attended a talk that Babbage gave when he was in Italy. And he took notes and wrote them up in French. And Ada decided to translate the French description by Menabrea into English. And Babbage in his autobiography says that Ada told him her plan to translate it, and he asked her, why don't you write it yourself? You understand much better than Menabrea does. He just went to a few lectures, and you understand completely. And she said the thought had never occurred to her that she should write something on her own of that nature. But then they agreed that she would add copious notes to the translation, which is what she's famous for. Basically, this one thing, the notes to the translation of Menabrea's description on an analytical engine, is why we hear about her today. So in particular, she worked out how the machine would solve, in this case, compute Bernoulli's numbers by recursion, and she was very proud of having designed this table and laying out essentially a program with a loop and so on to compute the numbers. And again, Babbage in his autobiography says that it was essentially all her work, this appendix, except that when it came to computing the Bernoulli numbers, he helped her out to save time. And we have some correspondence between them about this.
Who wrote these things? Who wrote what?
That was Babbage's autobiography.
Ah, that's Babbage. Okay.
Okay. So right. So some of the things before were from De Morgan's wife, and some of the others were just from magazine articles. Okay. So Babbage refers to Ada as an enchantress of numbers.
It was number, wasn't it? I think.
Sorry, yes. And today people say things like she was the first computer programmer, which is stretching it, because Babbage obviously, he wrote lots of algorithms, describes them, though maybe not in a format of a table. But you might refer to her as the first computer scientist, but she referred to herself as an analyst or a metaphysician. She was interested in the metaphysics of things. And perhaps it's best to call her the first philosopher of computation, because she devoted thought and wrote about the implications of what Babbage had invented. Okay, so let's go to the first question she raised. What can a computer calculate? So her answer was sort of everything. Now that's not technically true, we'll talk about it. She writes that this new machine opens up a vast and that there's a language now in which to express calculations and which can be computed, so that we can do things that were never possible before. Not just speedy and accurate calculations, but for purposes that were beyond mankind before this invention. Babbage appreciated her, and writes again that she seems to understand it, meaning the computational ability of the machine, better than I do. And she's far better at explaining it, but that she understood the significance in a way that perhaps he had not. And she writes that she points out what this invention was, which was Babbage's invention, had used the punched cards of the card loom as both to write the program and as an auxiliary storage. So because of these punched cards, it became possible now to do any calculation. Unlike the difference engine, which was designed for some specific calculations, this is had unbounded abilities, as Ada understood, that you can make any pattern, any mathematical pattern you might want to. So this is the Jacquard loom, and the same cards were to be used in this analytical engine to program. So she says that unlike the difference engine, and she realized that this was what we would say today is a quantum leap, something that's now programmable, can do arbitrary calculations, just like with the loom, you can make any design you like. Okay, so, and that we've gone beyond arithmetic. Once you have that ability to program with cards, we're beyond the calculating machine. Now, what did this machine have? It had sort of three abilities. It could do arithmetic calculations. It worked with decimal and steam engines and whatever, but it doesn't matter, it did arithmetic. It could make decisions. The program can say if something is or isn't on some card, do something. And it had a storage to store partial results. It had a memory on it could use new cards. So these are the three R's of elementary school: arithmetic, reading, and writing. So now Menabrea in his notes says that once you have the basic arithmetic operations of addition, subtraction, and so on, then you can do anything numerical. Okay, these lie at the basis of more complicated numerical calculations. You want to take exponents, do repeated multiplication, and so on. So these four operations, or we'd say plus some tests for equality and inequality, allow you to do any kind of arithmetic. So Ada says more. She says that because that you can do symbolic computation now, that you can do, it's unlimited in variety, that we've now connected the operations of the machine, of matter, with the mental processes of a mathematician, or with the most abstract thoughts of a mathematician can be translated into numerical calculations. And today people write that this observation shows us to have understood the principles of programming a century before others realized the implications. But the name with which the theory of computability is most associated is Alan Turing, whose 100th anniversary was recently celebrated. And he reduced the notion of what are the atomic actions that a human being can do when computing, when calculating.
Nachum,
Yes.
could you go back?
Sure.
That's it. One more slide.
I think what this means is that the ability of the program to combine mathematical arithmetic operations in arbitrary ways gives an unlimited ability to program any and all.
Do you go along with this sentence as it appears on the blackboard?
This connection between matter and abstract mental processes.
And the abstract mental processes of the most abstract branch of mathematical science.
Okay, so it's something maybe I hope to get to partly.
Yeah.
The relationship between there's a big question which Ada, I think, also plays a role in, which is how to connect these operations which work with gears and whatever, a mechanical process, with something else, how to relate the two. And I think this requires additional thought. So I'm not committing myself.
If I may be allowed,
Yes.
okay. In mathematics, we prove theorems,
Yes.
okay?
So today computers prove theorems, yes.
And you think they can prove stuff like
Do I think?
algebraic topology and so on?
They
Well,
can.
they have proved
Yeah.
algebraic.
Maybe. Well,
They've proved
so you go along with it. All right. Fine.
conceptual. Okay, this is an issue that's coming up again. So
Okay, fine.
let's not commit. Let me not. I don't have to commit, right? So Turing, unlike his predecessors, tried to analyze what do human beings do when they calculate, when they compute, when they work according to rules. What are the most basic operations? And he and Post at the same time understood that there are basically three things. There's the writing or drawing or doing something in a specific locations where your hand on the pencil is. That you can look at these locations to make a decision to see, did I write an A here, a B here, painted red, painted yellow? And that you can change your focus, that here you're writing on one box, move over so you can write in the next square, and the next square. And these, for Turing, described as the basic operations. So that's the drawing or the writing, the reading, which forms the basis of decision. Don't just look, but what you do depends on what you saw, and moving your focus. More generally, which is part of
What's this draw?
to write, to make
okay.
a symbol in
Okay.
a square. Okay. So let me skip this. I saw this year an ad for Lovelace lectures and so on, or Lovelace Day, actually, in October. And the claim was that she's the first person to realize that a general purpose computer could do anything, giving the right data and instructions. Okay, she did write the analytical engine means weaves algebraic patterns, and she says that you can compute anything. This is sort of like a similar statement in Time magazine 1980, 19 something or other, in which Bill Gates, first time he was on the cover of the magazine, I don't think the last time, but inside is a computer person, whatever, engineer, makes this claim. Put the right kind of software into the computer and it will do whatever you want it to do. There may be limits on what you can do with the machines because you have a limited budget, but there's no limit on what you can do with software. So this is the notion that we can solve any problem with software. Now, Turing, of course, long before that, showed that there are limitations to what computers can do. In particular, in this most famous paper of his on the Einschränkungsproblem, and that there are limits. The computer cannot solve all problems. So there was a previous talk in the series that discussed this, at least partly. And it's all based on your abilities as a contradiction. I'm a liar, I'm lying. And to formalize this in a way that the computer basically cannot, to put differently, the computer cannot solve any interesting problem about computation, about what computers can do. So because of this self-reference problem, not the topic for today. Back to Ada. So we need to formalize the notion of algorithm. If we want to say that 3 baskets of apples can do anything and everything that can be done, put aside those things that Turing showed cannot be done, but anything that can be done by 3 baskets of apples, then we need to formalize the notion of an algorithm, an effective algorithm, and in the time I have, that's what I'd like to do. So in a nutshell, and Yuri Gurevich was here back in December, and he spoke on this topic, so I'm going to be brief about it. So an algorithm is some kind of discrete, step-by-step process that the important thing is that one can describe how you go from step to step, and that the description is finite. It's in some language that we describe how to go about it, and that I can describe it to someone else, and then they could do it, and it's independent of the particular inputs. I'm explaining how to do it in general. That's what makes something an algorithm, that it's describable in some finite way. So the most famous algorithm, perhaps, is Euclid's GCD algorithm, and for him the computer was a compass and a straight edge. It was not one of these devices here. And here's the algorithm. Okay, it's a description, finite description in Greek, and it tells you how to compute the greatest common divisor. Okay. In terms of the operation of the machine, so when two unequal numbers are set out, he has actually two algorithms, one for whole numbers, for natural numbers, and one for real numbers. So these are two different things. But that's what we mean by an algorithm, something that can be described. Now I tried to think, though, what is the earliest non-trivial algorithm, long before Euclid. So I think when Eve came back in the garden with a basket of apples, she wanted to share them with her significant other, Adam. And okay, so she has some number of apples. This is her algorithm. She needs to know essentially nothing, no arithmetic. She wants to divide it evenly. So one for me, one for you, one for me, one for you, one for me, one for you, until there are none left. And to describe that, it says if there's two piles, you have three piles now. These are the three baskets I showed you in the beginning. Her basket, his basket, and the one she brought back from the garden. And so all she does is pick up an apple, move it from basket to basket until she's done. So the algorithm is trivial, but I really think that division is a more basic mathematical operation than multiplication. And it's non-trivial. Now, Ada again said that the analytical engine has nothing in common with anything that came before. Everything that came before was like a special purpose machine. This is something altogether different. It is universal. It can do anything. And I'm not going to force you to read every quote here. This one we saw already. Okay. Now, let's go back to Turing. So I said Turing said that the basic operations of this reading, writing, and moving, and he says here that in elementary school we learned to do this on a two-dimensional paper, on graph paper, near millimetry, and so something like this. That's what we do in school. And the teachers tell us where to put each digit in which box and to keep things right. So normally we work in 2 dimensions. Now, part of what Turing did is said, who needs 2 dimensions? One line is enough. I can put one line after the other, and that's what we call the Turing machine today. But in a sense, human beings work in 2 dimensions. So here's a 2-dimensional algorithm, from ancient times, and here's my 2-dimensional algorithm. Okay, so it's written down here. This program, just going back to Turing's original idea. Okay, you can say it's what the instructions say: walk right if it's red, paint it blue. Go right if it's white. Go back again. You can understand this is like a children's game. Any child can do this. And what it does is going to convert that number in unary, the number of the 9 or something red squares, into its binary representation. So that, and it's working on a 2-dimensional thing. It's just fun for me. I like that. And the program I'm most proud of as a Turing machine is this one that you can see running on the bottom. That little program over there, using just these operations of looking, writing, and moving. In this case, you can move up, down, left, or right, 1 square. That little program does this. So it draws a quarter of a circle, slice of pizza, just by these basic operations of looking and writing and moving. Okay, so, but what we want to if we want to analyze what can be calculated in the most general sense, and to say that anything that can be done by a human being calculating can be done by baskets of apples or Turing machines or anything, then we need something more general. We need not the specific set of instructions, not a specific kind of work place, not necessarily 2 dimensions, not necessarily 1 dimension, but we want something totally generic, and this is what Gurevich did. And I'm just going to briefly say...
Just put that back for a second.
Sure.
Read that quickly.
Okay, so if we want to understand... Okay, Post was arguing that people like Church were claiming that some specific way of doing calculations captured everything that could be done. He said, how do we know that recursive equations capture everything? Because we have other ways of thinking, many other ways. And how do we know that we've captured all possible ways of, creating a sequence of numbers or something, just because we have one method, namely recursion equations? Perhaps, we do. The brain works in can do many other things. How do we know they're all the same? And that's what he wanted. He said he wanted to understand. So we want to. So I said the definition of an algorithm is, I want to formalize the notion that an algorithm is something that its evolution, its step-by-step progress can be described in some finite fashion. Okay, so Knuth, famous computer scientist, said, algorithms were around, like in the Garden of Eden. Eve's algorithm was around long before Turing came along and formalized it, just like the number 2 was long before logicians came up with some set theoretic way of encoding, really, a number. Okay, so what then, if in the most general sense we want to speak about algorithms, firstly we're talking about what we call today a state transition system. You have a current state of affairs, and what the program does, what the algorithm does, is tells you how to progress to the next situation, to the next state. And if we don't want to talk about a programming language, we're talking about a state and its progress. So states and transitions, and the transitions are governed by some algorithm, by some program that is a finite text that explains what this relation is on states. So besides having initial states, where you start out with some initial state, you can go through other states, and you reach a point where there's no next state, then you're done. That's a terminal state. And okay, that was today. This is tomorrow, hopefully. Okay. That's a change of state. Now, the transition, the method has to be mechanical. We want methods that don't say, use your insight, guess, and we want the methods that each operation should be done, should only take a bounded amount of time. You can say, solve it, until you solve it. Look until you solve. That's not a kind of method we're talking about. We're talking about instructions like Turing described, single atomic steps that only take a bounded amount of time. So, we're not interested in all kinds of things. We're not interested in what happens after infinitely many steps. We're not interested in what happens if you use a roulette wheel to decide what to do next. Not if you can, and so on. Okay, so these are disallowed. Now, the state is what's changing. And so we want, so for Turing machine, so the state was that piece of paper with colored squares, and the next state is what I changed on it. And in general, those state can be anything. Well, Turing in a footnote, I think, says that the point of his machine is that you can go out for lunch in the middle. You can stop, you can turn it off and pause it, like you can do with the laptop. Put it on pause, go have a cup of coffee, return, and continue where you left off. So it's in a state that's fixed, sort of like when they invented pastels, the painter could stop in the middle and take a break. This is, I don't know, we all too common in computer science, we compare algorithms to cooking. I think that's not an apt analogy. If you take the souffle out of the oven in the middle, pas souffle. It is not like a Turing machine. Okay. You can see I'm in Paris this year. Okay. So, and we want this to be generic. In other words, if Church, I didn't say uses whatever terms representing recursion equations or lambda terms, Kleene, okay, never mind. Turing was using strings or elementary school graph paper, but we need something that's general and encompasses everything, and that's what logicians came up with the notion of a logical state, what they call a first order structure, what the state is described, or the salient aspects of the state of affairs is described by relations between its elements. And this is something Post already said in 1922, an unpublished work, so that you can completely describe a state by a bunch of relations. This is related to this by this relation. This is related to that by that relation. And that's what logicians invented. That's what we're going to use for a state. A state, then, is things you can do. I have a compass, a ruler, addition, multiplication, the abilities that are part of the state, and a memory, the things that are changing. Something was here in this moment, and the next step it's going to be someplace else. Okay, so that's what a transition does, is from the point of view of so a state has operations, and the operations relate. It says 2 plus 3 is 5. That's what the relation says. And what can change from one state to the next state is the meaning assigned to the operations, or to the objects that are being remembered there. So, anyway, this is all what Gurevich presumably explained. So states are the logical structures. All the states of a particular algorithm use the same language. They talk about addition. They use the same name for addition. And, okay, so a state also has a domain. It's working on numbers. It's working on letters. It's working on graphs. It's working on whatever the objects it's working on don't change during a computation. Okay. Let me get to the main issue here. I'm skipping a drop of technicalities. And getting to the main point. So we have states, which are these structures, and we want to say that we can describe a transition with a finite text. Okay, so the idea is that we want to be able to describe the algorithm as a clerical process of saying exactly what needs to be done in terms of the basic operations that we're given, and that can be applied to anything until we get the answer. Okay, no miracles, just instructions that anyone can follow. Okay, so this is what I find to be Gurevich's greatest insight, is that if you want an abstract way of saying that there's a finite description, say that what the algorithm does depends on only finitely many nameable things. So transitions are determined by a fixed set of terms, from the logician's point of view, of first-order terms that describe locations in the state, describe elements stored in the state, so that if any two states agree about these things that the algorithm presumably talks about, if they agree on the value, if they both say that 2 plus 3 is 5, and they both say that this square has 2, and that square has 3, then they both do the same thing. The same thing happens if the relevant things are the same in 2. Let me, just as a trivial example, if these are the terms, x and fx. These are terms. X has a value in the state, it's 3. F of x is 5. But f of 1 is not referred to by those terms in the state. So the idea is that we're saying that these two terms are going to fix the behavior. So if two states agree about these two things, they're going to behave likewise. What this means is if these two states agree, both have x is 3 and f of x is the same in both, then if this one changes x to 1, then this one changes x to 1. If this one changes f of 3 to 0, then this one changes f of 3 to 0. If neither of them talk about f1, so if f1 was 7 here, it stays 7. If it was 2 here, it stays 2. So they agree the changes are determined just by the agreement on that. This doesn't do, if this agrees, it cannot then, okay, f of 1 cannot go from 1 to 4 over here. This makes a change, even though it agrees with the others, it makes a different change. That's prohibited. So the idea then is that if there's an algorithm, and the algorithm has a finite description, then it talks about finitely many things, and anything it doesn't talk about can't affect what the algorithm does. That's the idea. Okay, so this is just pictorially, these two states, if we agree about everything relevant about tomorrow's weather, then tomorrow's weather will be the same. So Gurevich formulated this as three postulates of computation in a formal but very, very generic way. Algorithm is state transition system. That's what we're talking about. That's not. That we're going to use logician structures to capture the current state, the static state of affairs at any particular time. Closed under isomorphism that I'm not going to talk about. And the main thing that a finite set of terms and the value that states assign to those terms determine behavior. And then he proved that anything satisfying those axioms can be described in the simplest of all programming languages. And not only can it be described, but that the description is complete. It describes precisely one step of the algorithm. And he called that an abstract state machine. And this is all you need to know. There are assignment statements, every programmer heard of. Usual assignment statements, like that's an array on the left, or if you like. Conditionals, test something and either do something or don't. And do a bunch of things, finite number of things in parallel at the same time. That's all. And then a combination of these things can describe any single step of any algorithm satisfying those postulates. And so it's a completely generic notion of algorithm. This is just an example. So going back to Turing, it's a generalization of Turing's idea that now the states, instead of having a two-dimensional arithmetic book, you have an arbitrary state, and the state has locations, and locations have values. And drawing means that you take a color, it's in one place, and a color and put it someplace, like that. Paint that one black like that one. Looking means I can look at that square and say, if it's black, right, do something. And moving means that I can change my attention from one place to another. That means that I'm sort of changing the value of those terms that I said that are decisive. That's what the algorithm is looking at. It's looking at f of x, we said. So f of x now might be someplace else. If you change x, then f of x is elsewhere. And so it really is a generalization of Turing's insights. All this leads up to what we started with, the Church-Turing Thesis. I want to show that any effective calculation, anything that we can actually do, can be done by a Turing machine, or by what Ada said, Babbage's engine can tabulate any function, whatever. So this is her thesis, in my words. Okay, this part is my words. So she's talking about that this is a machine that can do anything. Okay, and why we want it. I'm skipping. Okay, so skipping part. So I'll skip one. So Hilbert was interested in the question of, can we determine whether a formula is always true in calculus, in first order predicate calculus. So we're interested in predicate calculus, whether things are true or false. And he wanted an effective method, but effective didn't have a formal definition. And this was the important problem. Poincaré compared that. What he wanted is a machine that works like the sausage factories in Chicago. Put axioms in one side, and theorems come out the other side. He was in favor. Halavai. Okay, so this Church-Turing thesis that we're talking about, it says that anything that can be done effectively can be done by a Turing machine, or as I said, can be done by the analytical engine of Babbage, or can be done by 3 baskets of fruit. Okay, so that's Church's thesis. And as Montague pointed out, we need a precise framework in which we can reason about it. And this, Gurevich's abstract state machine that I described, what an algorithm is a precise framework in which we can now address this question of what does it mean to be effectively calculable. So Church, in a letter to Kleene, says that Gödel thought it might be possible to express axioms that describe effective calculability, and so we have 3 of them already. Gurevich's description of an algorithm, it's a state transition system with states are first order structures, and the transition, it depends only on finitely many terms. Okay, so Schoenfeld, famous logician, tried, let's write down some axioms which we all agree on. I hope no one complains. I assume you agreed with the 3 axioms so far, 1 to go, and then perhaps we can prove the thesis, which is what we want to do. But Schoenfeld made some progress supposedly, but didn't succeed. Or maybe succeeded in the Go game. Okay, so why should we believe, before I prove it, why should we believe it? So one standard reason is that Church had this thing called lambda calculus, and there's the recursive equations and the Turing machines and Markov algorithms and Kolmogorov machines. Everyone came up with some way of programming, and then people proved that they're all equivalent. What one can compute, the other can compute, and vice versa. So, sounds good. That's not convincing, because maybe they're all one kind of computation, they're all related, but there's some systematic thing that we're skipping. And in fact, that happened. Originally, people thought that some weaker form of recursion was enough for everything, and it took a few years, and they said, no, there's Ackermann's function was. Okay, so that's not convincing. Another reason people give is that every programming language only computes what we already know we can compute. I mean, it's somewhat the same. But again, okay, so wait a few more years. Maybe we'll learn how to compute something we haven't. Maybe quantum computing, who knows. This is called the Turing tar pit. No matter what people have come up with, they're stuck in the tar, can't do more than Turing can do. Okay, that's what everyone says. Not convincing. Whatever one model compute, all can. The only reasonably convincing argument was Turing's, and everyone recognized that. That when he said, what can people do? All they can do is read, write, and move around. And if those are the atomic actions, and we can say that no matter how you combine those atomic actions, this is all you can do, that's more convincing. Okay, so, but what we want to do is take it, and Turing actually in the last part of his paper goes into careful explanation of why this makes sense. I'm not going to go into it now. So I want to take Turing's ideas, but generalize it so it covers any kind of computation, not just on paper, not just strings, not just working with letters, and not just with the operations that he has right move, left move, but more generally. Okay, so the main point.
Put that back.
Put that back. Martin Davis. Okay, so the question is, what basic powers do you have? What are you given with in the beginning? What can you do? If I give you the ability to do something magical, then obviously you'll be able to do something magical. So it all goes back to what do you have initially? What abilities is the algorithm endowed with in its initial state? So the initial state has operations, things it can do. It can do addition, do multiplication. What it can do later, it can learn to do more things. But if we start out with things that we don't know how to do, then, for example, I mean, take Euclid's computer, the compass. I mean, he can draw a circle in a way that maybe a Turing machine cannot go through every point on the circle, represent them all. All right, so no magic. We don't start with any magic. Okay, this is the Witch of Endor, none of that. So we came up actually with 3 different ways of saying that initially you're not given any supernatural powers. And 3 different ways of saying that all turn out to be equivalent. But the most basic is this. That we have some algorithms are constructive in the sense that you're not given any ability initially other than names for things. Like in Adam named every animal. All you have are names. You have no knowledge in your initial state, nothing beyond a way of naming the objects. And so you construct things by constructing a new name. Okay, this is what computer scientists call constructors. So these are terms, expressions, and we want each expression, each term in terms of these constructors. So the constructor is something like 0 and the next number, like in piano axioms. So you have 0, you have successor, and successive, successive, successor. These are your names for your numbers, and you're not told anything else. No addition, no multiplication, no anything, just names for numbers, which is a repeated successor. So, and it's a Herbert meaning you don't know anything about the relationships between different numbers. You only have one name for each thing. Okay, so if we concede that that is effective, that all you have are names for countably many objects, that the names are something you can work with, and you can build a new name by taking a name and adding another successor to it, then everything else that you can do with that is something that you can do. Okay, we know how to program it, we know what an algorithm is. So anything that we can build algorithmically, given only constructed names for things, is certainly effective. And that's all you need. Okay, so besides the successors for natural numbers, you can have more interesting objects like binary trees, where you have the empty tree, and you can build trees of trees. And so we can prove, which I'm not going to bore you with, and I don't have much time left, that anything that's constructive is equivalent in power to a Turing machine. Can do no more, no less. And back to Ada. I skipped over something, I hid something which I think is crucial, and that's the question of representation. So we say start out, you have numbers, and all you do is name numbers, and based on that you can define addition, define subtraction, define equal, you can define everything in terms of just that. Therefore, anything you do is effective because we know how to make a name. Now, Ada, which is one of her great insights, I think people agree today, is that she said that it's a mistake to think that just because Babbage's machine works with numbers, it only reasons about numbers. That because it's arithmetical and numerical, that anything it does is arithmetical and numerical rather than symbolic, algebraic, or analytical. That in fact, she says, the engine can arrange and combine numbers as if they were symbols. And therefore, she opened up the world to computation domains other than numbers. And so we could actually print formulas, or print some encoding of formulas. And she was, okay, she says that we're not going to bother actually printing it, but we could. And it's a mistake to think that just because we use some particular notation, that therefore what we're doing is numeric because we're using numerical notation. In fact, it can be. And then she talks about music and other things that we can compute. Okay, and so this science writer says that Ada understood better than Babbage that it's not just about numbers. That you could have words or formulas or music or anything that can be expressed symbolically or can be expressed as a number, where we're thinking about something else. So this is the issue of a correspondence between things we think about, perhaps, and the numbers that the machine is spitting out. And I think this issue of representation is crucial, and that we ignore it too often, and we ignore its implications. So I'm going to tell you a few words about it until someone stops me. Okay, so A, B, C, D, just the computer says 1, 2, 3. I'm thinking A, B, C, D, so I can write a sonnet. And this is how, in fact, computer scientists, when I said that all these different models of computations that different people invented are the same, they only show that they're the same in the sense that one may work with numbers and another with strings, with lists of digits, but I know how to relate them. So I don't know, the technical things, Gödel numbers, church numerals, and so on, doesn't really matter. That where a numeric machine is spitting out numbers, a Turing machine may be writing letters. But I can use, 1, 2, if I have 10 strokes, that's for me the number 10. So it's only in that sense that we show they're equivalent. Okay, so the question, we have this relationship between two different worlds, like numbers and strings. Let me show what I mean. So suppose we want to work with graphs, okay, but our machine works with numbers. So we can say, okay, that's graph, and I just made up these numbers. That's graph number 1, that's graph number 2, that's graph number 3, and we gave them names. Now we have operations on graphs, though. Sorry. Okay, we can have add an edge. So these arrows are adding an edge, adding different edges. And so if while it means going from here to here is adding the bottom edge, that corresponds in this arbitrary representation to going from 3 to 4. Okay, so this is, we can call it a tracking function. We have two domains, say numbers and graphs. The graphs up here and numbers here, and we represent a graph by a number. And what we want is that the corresponding operation on numbers, I mean the add edge here for numbers corresponds to adding edge to a graph. And this says that this function on numbers tracks that function on graphs. And the only requirement I want to make is that this is an arbitrary injection. It doesn't map two things to the same. And even that can be weakened. Okay, so that's how we can work with one thing and think another thing. And that's what people do all the time. So this is called computable algebra in the sense that if those operations on the bottom are computable, then we say that the algebra, the operations on top in the abstract kind of world are computable. So this is the way to relate, say, states of mind or something with states of a machine. Okay, so back to the Church-Turing thesis, I skipped over something, which is suppose we're working with numbers. We're computing a numeric function, but we don't use numbers at all. We use graphs. You can write a program like this. So C is some graph. G is something like add an edge to a graph of some kind. P is some kind of test about a graph. Is it I don't know, complete graph or something? And so all these operations, P, G, and C, are graph operations, and still I can use them to compute a number. I can say f of n is the minimum number of times I have to do G in order to get something satisfying P. So I need to say not only does my machine work with a machine that works with numbers is effective, but also one that works conceptually with graphs. So, but we just have this notion of computable. So we can say that we can, any machine, any graph machine, no graph machine can do more than a numerical machine because there's a way of translating graphs into numbers, such that whatever that graph machine does in terms of its constructors of graphs, its ways of building graphs, its basic building blocks, corresponds to a numerical number. So the moral is, provably so, Turing machines can simulate up to an isomorphism any model of computation that satisfies the four axioms we had, Gorevich's notion when the algorithm is plus that everything that's in the initial state can be built out of constructors. Though the machine works in some other domain, we have to use this notion of tracking of a representation. More than that, you can show, which I haven't said anything about yet, that there's no way of representing, say, the strings of a Turing machine, no way to change domains and do more. This is an issue. So no representation can an effective model do more than a Turing machine can. And in fact, it's just no matter what domain you're working with, if you have constructor functions, they're all equivalent. Everything you can compute in one has a mirror image used in some other representation for the objects of the first. Who's in charge of time here?
We've got up to the 12:30 mark.
Perfect. And beyond. Oh. Let me. I plugged in the speakers for a reason. So Turing is also famous for talking about a universal machine. Once you have this notion of representation, that you can represent one object from one world as an object in another world with no restrictions here. This all we said has to be an injection. then you can represent programs as numbers or programs as, I don't know, in some other way. And once you can sort of give a representation to a program, then Turing said that we can have one machine that can do anything by sort of the Jacquard-Loom program, these holes. They are now an object that we can work with. That's an idea of a universal machine. Let me just say, I had this fun programming language that I'm trying to, they have two-dimensional Turing machines in the museum across the street. A few samples of working in 2 dimensions, which I think makes all the difference between Turing machines being understandable to almost anybody, my granddaughter, and to what we teach in school, which no one understands. Okay. So here is a universal Turing machine for this 2-dimensional Turing machine language that I played around before. This is a universal Turing machine. And it's easy to understand once you look at it. Here's an example of a bubble saw. Okay, so this, instead of having the chutes and ladders connecting things, drawing these arrows. So this is a program for sorting. And you saw the universal Turing machine. And so that program that universal program looks at the sorting program, goes down to this, whatever here, 4113. It keeps its place with these red dots, and slowly, I need to speed it up, but it's slowly making its way around, and in the end it's all going to be sorted. Oh, this is a little too slow. Okay, so that's a universal Turing machine, and that's Turing's idea. So,
Doesn't the Turing machine need an infinite tape?
it needs unbounded tape.
Yeah.
Unbounded.
This is bounded, right? In the picture we saw before, it was bounded.
Yes, okay, I agree. So anything, if you bound things, then you can hardly do anything. I agree. I think the human mind is a finite state. The automaton can't do anything more than trivial things. But when one says that Turing machine can do anything that can be done, a Turing machine with unlimited resources, not infinite, it just has to. They have to add, plug in a new diskette, disk-on key, whatever.
So the tape was not part of this picture.
The tape was part of the picture. When you say, because the tape
It was
is part
just
of
an
the picture.
example to sort 4 numbers, right?
But so when in the abstract way I'm saying, okay, you have 0 and you can and you say next, 0, next, and these are just names. It's like there is no limit, there's no biggest number, we say. So that's all it means. We have names, conceivably names for every number, and therefore I remember when one of my kids said, well, we only have finitely many words and infinitely many numbers, how do they work? So you can make up new names for new numbers. That's the equivalent of the infinite tape here. It just means that you can name something, and of course we can't really name something that's too long. So that's all that's going on. So if you can name arbitrarily more and more things in your presumably countable domain. All right. Well, so there's a topic today called hypercomputation. People try to think, well, maybe we can go beyond the Church-Turing thesis. So, Martin Davis, the physician computer scientist, we can't exclude the possibility that someday some alien is going to show up and she's going to be able to do more than we can.
On what occasion was this picture taken?
Do not remember. But I can find out. Sorry, it was
A formal occasion.
formal occasion, yes. Probably got an award of some sort. Wedding? Could be a wedding, yes. Right.
No, it could be getting a prize.
Well, it could, right. All right. So Robin Gandy, Turing's student, had this, said that we can distinguish between two, what we did until now, asked what can one do by means of calculating, pen and paper kind of calculation. But if we want to ask what can some device that we can build do, so one can raise the thesis, which is different. It's sort of physical thesis, saying that we cannot build anything that can do more than a Turing machine. Anything we can build, any device we can build, can only do what a Turing machine can do. And that's a completely different question. However, and then various people think, for example, either the brain or some device might be able to do more. The human brain can do more than a Turing machine because it has some ability that goes beyond the Turing machine. And the point then, if you believe this kind of thing, then you have to say that one of the 4 axioms I gave you is not obeyed by the human mind. Because if it obeys all of them, provably you can't do more than a Turing machine. So, and any of these people who think otherwise, tell me exactly which of the axioms you're violating, and you can analyze them. So there is some suggestion to use a black hole. You shoot a certain kind of black hole. I don't remember which variety of a black hole. You can shoot a rocket there with a computer on it, and and in finite amounts of time, from our perspective, it goes through an infinite number of steps. And you tell it, when the program halts, send a signal back home. So if we didn't get a signal, time's up, no signal, it didn't halt. If we got a signal, it halted. If you can build it according to physics, or according to Newtonian physics, you can also build devices. So take your physics, but then you know which axiom is being violated. Back to Ada. No. If we're comparing models, which we've been doing, I want to say that this model, with the black hole, is more powerful than a Turing machine. Well, how do we compare? If we want to be formal about it, we need to say exactly how do we compare the power of different mechanisms, different formalisms. Okay, now I'm getting back to my baskets of apples. Okay, so this is technically called a counter machine. Okay, so you have all these kind of counters. Okay, the worry beads, misbachas and so on. Okay, many cultures have these counting beads. Now, okay, so if you have one string, okay, my granddaughter had this. Okay. In kindergarten, you string the beads. So these are like the baskets. Same thing. You can add one bead, remove one bead. The advantage here is that usually you string them one at a time. And we can say, well, can you do more with 2 strings than with 1 string? Can you do more with 3 strings than 2, and so on. So, okay, so is this more or less? I mean, not less for sure. Okay, so it is provable that with 2 strings, one cannot compute 2 to the n. In other words, you start out one string has n beads, and when you're finished with your algorithm, that all it does is adds and removes beads and check whether the string is empty. That's all it does. Then you cannot end up with 2 to the n beads on the string in the end. Also not n squared. So with 2 strings, you cannot compute 2 to the n. 2 baskets are not enough. You need a 3rd basket. If you have a 3rd basket, then you can compute 2 to the n. Now, 4 baskets don't give you any more than 3 baskets. This we know. 1 basket does less than 2. 2 does less than 3. 3 and more are all the same. In the sense of, you can have a starting number in a basket, and then you have an ending number in the basket that gives you a numerical function. And what functions can you compute? So never mind how you prove this, but there's an issue here. Okay, you can prove it. The issue is, are 2 strings more powerful than 3 or not? I said, sorry. Minsky, who explored these things, did show, however, that with 2 baskets, you can always, if you start out with the 2 to the n apples, okay, the Garden of Eden was plentiful. You start out with 2 to the n apples. You can for any computable function f, you can compute 2 to the fn. So in the sense that we're talking about representation, if you represent the number n as 2 to the n, then you can compute anything with 2 baskets. So in one sense, 2 baskets cannot even compute n squared or logarithm or various other things, but they can if you represent numbers in this funny way. So a finite state machine with 2 counters, that's what we're talking about, this is Wikipedia, is equivalent, Wikipedia says, to a Turing machine under this representation. Now I think we lie to our students in class. We teach them 2 contradictory notions of computational power. We tell them that, to be technical for a minute, that primitive recursive functions are weaker than recursive functions because primitive recursion does not include Ackermann's function. It's a subset on the set of functions. Then we tell them that the two counters are equivalent to Turing machine. Oh, we don't say that. We say that recursive functions are equivalent to lambda calculus, are equivalent to Turing machines, are equivalent to something else. All of them under some simple and not simple representation. So we say that representation preserves power, and we say that being able to compute fewer functions is weaker, but then a two-counter Turing machine can do more than can compute more than itself. Two-counter machine cannot compute 2 to the n, cannot compute x squared. Under representation it can. So in one sense, it's that 2 is as powerful as 3. In the other sense, 3 is more powerful than 2. Can't have it both ways. So the right way, I think, is under representation. Because we do that all the time, and that's back to Ada. So, as it turns out, if you're not careful about matters of representation, you can show that for any set of problems, any formal language, any finite number of formal languages, or even more, a finite state automaton, the Turing machine, or to say you have a limited tape, can do everything under a representation. You can represent every string as under a bijection. This is a technical thing. There's a bijection between string and string that will make undecidable problems regular. So you have to be careful. All right. I just want to say a few more things about other things we're interested in this context. So complexity. So Ada said that the engine can compute any indefinite function of any degree of generality and complexity. Let me talk a word about complexity. Okay, so Menabrea said, well, some problems you might need 20,000 cards. So at least in the beginning, Babbage was rich, and then later he got poorer. But once we have this notion of what an effective effective computation is, we can prove more. We can prove what's sometimes called the extended Church-Turing thesis, which says that not only can a Turing machine compute everything computable, but it doesn't take much more time than any other way of doing things. So there's something called the RAM, random access machine, which for a Turing machine to simulate that takes some quadratic or it takes a cubic. A Turing machine with one tape takes a cubic amount of time more than this RAM. But we can prove. Okay, so everyone who works in complexity uses this model of computation called the RAM to measure how many steps it takes to do some kind of computable thing. So the extended Church thesis claims that on all reasonable machine models, the relationship between them is polynomial. But actually we can prove that the relation is a very small polynomial, because now we have a formal notion of what an effective device is of any kind, that includes all programming languages and all data structures that are constructible. And we can show that a RAM can simulate any of them with almost no overhead. Okay, so now we know not only can a Turing machine do everything that's computable, but it can compute it with low overhead. Okay, so we can now spread out. Until now, this is classical notion of step-by-step computation. Today, computer science has advanced. We have parallel machines and cellular machines, interactive machines, analog machines, and other things. And so, where are we in these projects? So, Gurevich and Andreas Blas investigate extending their postulates that they mentioned from what we were talking about, the sequential device, to parallel and concurrent. And I spoke to you about going, what needs to be added to say computation is effective. So student Jenny Falkovich extended this notion of effective to parallel. So we can say the same thing, also this extended thesis, that a parallel RAM can simulate any effective parallel computation that obeys certain reasonable axioms. And we're working on going this along to analog. So the brain is different. Turing says, and Copeland said, that there are things that are not digital, that they operate in continuous time. The state changes over time. What does it mean then to be algorithmic? What does it mean to be effective? Something we're thinking about. And, okay, so now, so a cellular device, okay, this is a cellular automaton. You have all these, you have the plane here, you have pixels, and each pixel is running the same algorithm, and all of them are running in parallel. And the point then is that this is any effective parallel cellular device like this can be simulated by PRAM. So it's the same thing. It's a parallel process, and we need that its transitions to be described, or we need the transitions to be describable independent of which cell you are. So it's saying that they're all running the same program, but we need to include the notion of childbirth, that one cell can beget another cell. Okay. And, all right, we can do that. I'm not going to. So the bigger picture is the world, and this notion that the universe, perhaps, the whole universe operates under a fixed finite set of laws of physics, starting from the particle physics, which is a simulation of the beginning of the Big Bang. Things are starting to extend. So you ask the physicist, okay, he has various laws of physics that determine the evolution of the system. As Galileo said, that the philosophy or the world is described in the language of mathematics. He was talking about geometry here, triangles, circles, and so on. But the point is that you have, again, a finite description of what's now evolution in continuous time, or if time is continuous. So from that point of view, we want to also describe systems of things. You want to be able to have algorithmic descriptions on the molecular level or on the cellular level. I'm having fun.
As this plant cell, taken from a lily, prepares for division, the chromosomes first condense.
All right. So you have many different levels, and each level is usually described in some kind of finite terms. And we'd like to develop a notion of effective descriptions on multiple levels of interacting parts where they do communicate one with the other, and they each might work on their own time scale and in continuous time. That's the plan. We have another level of the organism. These organisms are cooperating according to some behavior. This is starlings. And the social biologist has equations for swarm behavior of some sort. And, okay, I don't know, okay, I have more. More complicated cases when things are interacting. This is Uber cars having trouble managing this kind of intersection. And, but again, if they're expressible as rules, then we would like to put them in this kind of family. To conclude, Ada, the third question, which I'm not going to talk about, is what is a computer being original? Is a computer doing anything on its own? She said, no, a computer only does what we program it to do. And okay, it's this idea that the analytical engine is aware, No, she said that the analytical engine is.
I can't
sorry.
parse that sentence.
No, so she's saying, I'm sorry, I missed her. She's saying that this new invention, the analytical engine, is as different, is as out of this world in her time as the notion that there might be a thinking machine, that a universal calculating machine is different, and no one has thought of such a thing, just as no one thought possible the idea of a thinking machine.
So did she
No,
think of the analytical engine as a thinking
No,
machine
she
or
didn't.
not?
She did not. She says, I think, okay. So she says that the analytical engine has no pretensions to originate anything. It can only do what we tell it to do. There's no possibility of anticipating consequences, she says. Turing didn't like that. He writes that her Lady Lovelace's objection says the machine can never do anything really new. Or one might say the machine can never take us by surprise, which is not the same thing. And he says, yes, the machine takes him by surprise, especially when he makes mistakes. I think that's a lame argument. So this is Ada on her deathbed, her mother's sketch. This is her daughter, so sometimes mistakenly thought to be Ada. Apparently it's her daughter. And I just noticed that the popularity of the name Ada, so in Hebrew it's Ada, but in English it's Ada, is beginning to increase again. May her memory be blessed. Thank you.
There's a pause for lunch now. You're all welcome to come back to this room in an hour's